normalized system, really, the normalized impedance. And anyway, the solutions are up there. Those quizzes were basically homework problems. I took a homework problem, and I think I changed the frequency on one, and I think I changed the value of the load of the other. They were very straightforward problems. If you want, we can go over it. But overall, the quiz average was pretty high. So I was happy with that. If you want me to, I'll go over it with you. But we're on S parameters now, and S parameters is something that you're going to see over and over and over again. And I started on Friday to explain them. So I'm going to sort of do a recap, and then what I also want to do is probably on Wednesday give you your your project, tell you what it is, so you'll have time to get started and work on it. Some of you will get it done over Thanksgiving break. I have to say that I'm going to ask you to do something that involves MATLAB in this one. Dr. Wentworth's kind of the person that requests this, so it'll be a project that requires MATLAB, and it'll require you to do something a bit novel. I'm not sure exactly how I'm going to do it, but I'll get this to you probably this Wednesday or at the latest this Friday. Okay? So before I start, any questions about anything? Okay. Back to S parameters. I'm just going to review this and go through some examples. So when you have S parameters, generally we talk about V1 minus is equal to, really it's going to be S11 times V1 plus S12 times V2 plus, and then V2 minus is equal to S21 times V1 plus S22 times V2 plus. And this is a simple two-port, so here, this would be port 1, and here would be your S parameters, and this would be port 2. And here we have an incoming signal, V1 plus, and we have a reflected signal, V1 minus. We have an incoming signal, V2 plus, and transmitted signal, V2 minus. That's the way, and this is only a simple two-port. Now let's do the extended to N ports. You can literally have N ports or N transmission line connections. If it was a 3-port, then this matrix would be 3x3, 4-port, 4x4, and so forth, right? And this is the way it's done all the time in the S parameters. They're used to measure devices and characterize them over the microwave frequency. Now, some of you told me you've seen them. I know that you've seen the basic current gain parameters, the H parameters for a bipolar transistor. I do know that because I checked on it. However, you probably aren't real familiar with a lot of these things. Now, what you're going to find out, and I'm just telling you this, give you a little insight that will help you later on. When you talk about parameters, they're things that define input to output. They can be done in terms of current, voltage, or impedance, or admittance. I'm just telling you this. Now, when you have any of these parameters, there's A, B, C, D parameters, H parameters, S parameters. S parameters are always in terms of voltage. And any of the other things, there are translations where if you have one set, you can get the other set. If you ever have to use S parameters for designing or optimization, change them into A, B, C, D parameters. You'll see, we'll talk about this later. It'll make your life a lot easier. I'm just telling you this is from personal experience. But he does not mention this in the book. He just tells you what they are. So I think, now, did anybody look at the S parameter section? If you did, I'd like to see. I had a feeling not many people did because the quiz was not on S parameters, so it makes sense. What I'm going to do is start, I want to go through an example we did, and I'll start talking about reciprocal networks and lossless networks and things like that, but I'll tell you the easy way to do that too. So, let's see. We're going to go through, we'll start with the simplest problem, and again, I'm doing this only so we can come up to speed and everybody will understand what's going on. This is the simplest type of problem. I'm going to have a characteristic impedance here, this is port 1. And this is going to have a characteristic impedance of 50 ohms. Then over here, I'm just gonna have a 100 ohm resistor. And over here, I'll have the characteristic impedance as E naught of 100 ohms. Now, I'm sorry, 50 ohms. Now, that doesn't have to be the same as this, but it would, most of the time, it's the same on both sides. Most of the time, it'd be foolish not to have that the case. So we're gonna get the S parameters for this. This is port 1, and this is port 2. How many remember, at least to get these things, there are things that are reflection coefficients with matching on the loads on the other side, so there's no reflections. And then there are transmission coefficients, correct, class? So what I always tell people to do when you do these, first, you realize that S11 is V1 minus over V1 plus, assuming the V2 plus is 0. Now, what that really means in a nutshell is this. If I have this matched, if this right over here is going to something where you can assume the load is 50 ohms, there's no reflections. If this, for instance, if a wave came through here, some of it's transmitted, but it hits and reflects back, then V2 is not equal, V2 plus isn't 0. You all follow me on this, class? If it was a short circuit, couldn't do it that way. It has to be into a match condition, so V2 plus, there is no reflected wave back into the port. You all with me? All right, so for this one, if that is the case, this is really just the reflection coefficient of port 1, assuming it's matched. You all follow me on the thoughts on it? All right, so looking at this, now I'm going to get the effective, and by the way, this is a symmetric network. And by that I mean that if you look at it this way, it is identical to the way it looks this way. You all follow me? It means you only have to find half the parameters. You got the other two. S11 will be S22, and S21 will be S12. All right? Follow me on the thoughts on that? This would be called a reciprocal network, by the way. Wow. No, sorry. Anyway, how do you get that? How do you get the reflection coefficient? Well, which is S11. Well, it's always what the impedance you're going into, correct? And if you look at port 1, over that way, this looks like you have 50 ohms, right? Then you have 100 ohms here, and you can model that 50 ohms as just a resistor, as it was 50 ohms. You all follow me? Class, can you also just, so over here, it looks like I'm going into 150 ohms, and I came from 50, correct? So whenever you're talking about reflection coefficients, the impedance you're going into, I'll just call it Z2, minus the impedance you came from, Z1, over the sum Z2 plus Z1. So for this one, Z2 is 150, right? Minus the impedance I came from is 50. The sum of those two is 200. So this has a reflection rate, reflection coefficient of really 1/2. Y'all follow me in that class? Everybody? All right, now, the transmission coefficient you can get a couple ways. Well, we'll get this will be S11, it will be S22. Now we need to get S21, and it's important you appreciate this. When I'm talking about S21, that's equal to V2 minus over V1 plus, assuming assuming V2 plus is 0. So what this is, the forward voltage gain. If you look here for a second, if I take V1 plus and I multiply it by S21, I find out what this voltage is, the waveform coming out of that port. Y'all follow me on that, class? That's an important characteristic. It's the forward voltage gain is really what it's called. So over here, the way I get it, first I need to get the transmission coefficient, port 1. And one way to get that is what? 1 plus the reflection coefficient is the transmission. You can do it that way. It would be 1 plus 1/2, which is 3/2, right? Well, put it 1.5. You can also get it by saying it's 2 times the impedance you're going into, 2 times Z2 over Z1 plus Z2. I'm doing it both ways just to show you if it works. This is going to be twice the impedance I'm going into is 150, isn't it? I'm looking over here, and I said this has an equivalent of 150, right? So it's 2 times 150 over 1. Over really the sum of those two, which is 200. So that's 300 over 200, or it's gonna be 1.5 as well. Either one will get it to you, but that's the transmission coefficient. Now what that does is, it tells me that if I have a signal coming in here that's V1 plus, the voltage here, this is not on this side, not where the transmission line is, just on the other side. Because remember, when the wave comes in and hits, some of it is reflected, right? What's left on the other side is actually gonna be that transmission coefficient times V1 plus. Everybody okay with that? Can you all appreciate that? Now of that, not all of that gets out. What happens is there's voltage division here. You all see that, guys? It's just, think of the voltage here is now divided. So it would be divided by 50 over 150. So that means when I actually look at this quantity right here, that's going to be equal to the transmission coefficient, right? Then it's going to be times that voltage division, which is 50 over 150, or 1/3. So that means I have the transmission coefficient is 3/2, right? And then that is going to be 1/3, or this is also going to be 1/2. And that will be S12 will be S21. Y'all follow me on this, guys? The reverse gain will be the same as the forward gain. So the S parameters for this simple problem would be equal to just 1/2, they're both 1/2, well, sorry, yeah, 1/2, 1/2, 1/2, and 1/2, which is about as easy as it gets. All right, it's a simple example. Now I'm gonna add a little complexity so you can appreciate the difference that happens. I'm gonna do it based on problems he has in his book too. I like to use his problems because he's got the solutions worked out in detail. I mean, they're right there. So this is example 10.6, where now we have still just basic resistors, but now we have a non-reciprocal network, something that isn't symmetric, doesn't look the same going forward or backwards, but it's just resistors, which makes it nice. So work this one with me. And for that one, he has characteristic impedance of 50, and he has 25 and 50. So the actual network he has is just a 25 ohm resistor and a 50 ohm resistor in parallel. And then it goes to the transmission line, and this transmission line is 50. And over here, it comes back, and it has a value of Z0 equals 50 ohms as well. And this is port 1, port 2. So see if you can do this with me. Work with me on this one. First thing I'm going to do is look at port 1 first, right? And I need S11, the reflection coefficient, which is V1 minus over V1 plus, assuming V2 plus is equal to 0, or it's matched. So that's the reflection coefficient, right? How do you get the reflection coefficient at this port? Now think about this. What does this look like, really? Well, from this side, I'm coming from 50 ohms, right? So I have Z0 equals 50. Then I look in here, what do I see? I see 25, right? But then I have 50 in parallel with 50, so 25 as well, right? Everybody follow me? So this is 25, 25. And when you look at that, what's the reflection coefficient? Now just think about this. It's as obvious as it seems. What am I going into? What impedance? 50. Where did that come from? So 50 minus 50 is 0. That's nice. That's what we like to see. So it's 0. Y'all understand the reason? All right, now, if that's 0, what's the transmission coefficient? 1 plus 0 is 1. Makes sense. Nothing reflected, everything's transmitted. This should make sense to everybody. Now, of the signal transmitted, how much of this signal that's transmitted is developed over here? Simple voltage division. Take V1 plus, right? All of it's transmitted. And then what? It's just 50 over 100 times that. Correct, class? So that means when I look at this, S21, which is V2 minus over V1 plus, what I have to do is find the transmission coefficient, which is 1, then times the voltage division, which is going to be 1/2, so that's equal to 1/2. Does everybody follow me? The reason. Think about it just by yourself. Make sure you can convince yourself. Y'all follow me on this? When I take a look at that V2 minus over V1 plus, it's how much gets out that port compared to what comes in. Here, how much comes in here? Well, that's V1 plus. Of that value that comes in, because the transmission coefficient is 1, exactly what? 1/2 of it's developed here, because that's 50 in parallel with 50. So it's a half. Y'all follow me? Right. Now, what about the second port? Looking this way. And work with me on this one, because these are where people get confused. All right, so when I'm looking this way, now I want S22 first. And S22 is V2 minus over V2 plus, assuming V1 plus is 0. So the first port is matched on this side. Let me erase that. So what does that look like from port 2's perspective? Well, I come over here and I have to see what this looks like, right? So I have 25 in series with 50 or 75, right? So I have 75 ohms, and what? That's in parallel with 50, isn't it? Make sure you see this. And it's coming from 50 though, right? The Z0 over here is 50 ohms. So when I take a look at that equivalent and I want the reflection coefficient there at port 2, what is it? Well, I need to take the parallel combination of those two, don't I? So what is that? Well, it would be what? 1 over 75 plus 1 over 50 is a good way. That's the way I do it. And you can do it your own way. And what's that going to be? 30 ohms. And you can prove that to yourself. This is really 30 ohms. So I'll put the equivalent right here. 30 ohms. And it's coming from a value of, you've got a value of 50 over here. So that means what? S22 is going to be what? Impedance you're going into, which is 30, that's correct. Minus the impedance I came from is 50, over the sum of those is 80. So that's what? Minus 20 over 80, or minus 1/4. Is the reflection coefficient. Do y'all agree with that, class? Okay. Now, of that, I'm going to go ahead and get the transmission coefficient from port 2, and that would be 1 plus reflection coefficient 2, which is going to be simply 3/4. Y'all follow me? All right, convince yourself that that's correct. All right. Y'all got the reflection coefficient, right? It shouldn't be a problem. You guys should see this fairly easy. It's simple resistors. Okay, now, when I want S, think about it. That's 2-1, S12, which is V1 minus over V2 plus, assuming V1 plus is 0. What's that actually going to be? Well, now I take a look at this. I said if I have a wave coming this way, and this is my V2 plus, right? The amount of that is developed right here is going to be V2 plus times the transmission coefficient, right? Y'all follow me on this? Can y'all see it back there? All right, now of that, how much is developed over here? Well, I take that and then I use voltage division. I take 50 over 75 times that. So I can say my S12 is going to be the transmission coefficient at port 2 times, and that's going to be 50 over 75, so that's what the transmission coefficient was. Port 2 is 3/4, so it's 3/4 times, and 2/4, and that's gonna be 2/3, right? So that's 1/2. Correct, class? Y'all agree with that? All right, so now we can say that when I get the S parameters for this network, and this is in the book, I have S11 is 0, S21 is 1/2, S12 is 1/2, and S22 is -1/4. And that's the S parameters for that network, just by doing simple analysis. Let's see what he has. 0, 1/2, 1/2, -1/4. This is on page 562 if you want to take a look at your books, just to show you. Does everybody follow me on that? There are some things he's going to talk about, lossless and reciprocal networks. I really don't worry that much about that. That's not something that I use in any way, shape, or form, but I'm going to mention this. Now, what do you think would be the easiest way to tell if a network is lossless or not? I'm just asking. Well, let me ask you this. Is an inductor lossy? In other words, does it dissipate energy or power? No. Does a capacitor dissipate energy or power? Does a resistor? So if you see no resistors, just capacitors and inductors, it is lossless without doing anything else. You don't need to do any kind of, it's some of these S parameter things. You're going to see it's S transpose times S conjugate. If they're multiplied together and it equals the unitary matrix, which I'll show you, it's just ones on the diagonal and zeros everywhere else, it's considered lossless, but just look at it. So there's no resistors, there's no problem. Now, if you're doing tests and you get a whole bunch of S parameters, then you have to do the other thing to see if it is lossless. Generally speaking, there are no absolutely lossless networks, but there's a lot that are very close. So just remember that in the real world. That's just something. So what he's going to say is, first, if it's reciprocal, it means it looks the same way forward and back. If S transpose is equal to S, it's called a reciprocal network. Now, the easy way to do it, in my opinion, if it looks the same one way as it does the other, all right, if it's just like ours, doesn't matter which end you're looking, it's the same, then it's reciprocal. That's simple. Now, you can do this if you want to prove this network, but I don't spend much time on this because I don't do it. For the lossless case, there are times, this is on page 577, when you do a lot of measurements, you want to see just how close you are to a lossless condition. He has it S transpose times S conjugate is the unitary matrix. So if you want to check out that data you measure, if you want to see if it's lossless, you're wondering if it's lossless, then you do this. Simply take S transpose and then multiply that times S conjugate. And if that's the unitary matrix, it is equal, it is in fact lossless. Now what is the unitary matrix? It's just this. It's 1, 0, 0, 1. And if it was a 3 by 3, it would be 1, 1, 1 on the diagonal, zeros everywhere else. Y'all follow me on that? And that's it. And that tells you if it's lossless. So the resistive networks, you'll never get that. Any resistor, it will never come out. But if you're doing measurements and you're trying to design, something so it's fairly lossless, and you got measurements, then you can do this operation mathematically very quick with modern equipment to see how close you are. It'll never be perfect, just remember that. Usually, they also talk about return loss and insertion loss. I'm going to do a bunch more problems, but I'm just trying to get the concepts out. So, return loss and insertion loss are on page 564, and as you've already had return loss, I think. Remember we talked about that with Shields, didn't we? Or was it insertion loss? Okay. So, when we talk about concepts of any type of loss that will be recorded in dB, and he has this for any given port, but in his book, when you talk about return loss, this is just a measure of how good a system is operating. You'd like to have really no return loss. That's the idea, no reflection. So what is it? Well, the return loss is in dB. And it's minus 20 times the log of the magnitude of the reflection coefficient at that port, which would be at port I. So if the return loss at port 1, it would be this. Return loss, it would just be the magnitude of the reflection coefficient at port 1. But what do you notice about this? If the return loss, if the reflection coefficient is 0, what happens? What's the log of 0? Minus infinity, isn't it? And that would make this thing go to plus infinity. Y'all follow me on that? So just keep that in mind. But this is a measure of return loss, and he shows this, and it's assuming a matched port on a secondary. He shows this in equation 10.29. Insertion loss is similar. And when you do insertion loss, it's in dB as well. Same basic idea, minus 20 times the log. Now he doesn't put the parameters, the S parameters, but I like doing it this way. Insertion loss of the, he'll put IJ, but of like the 2,1, S21, it's just the magnitude of S21 right there. Y'all follow me? Now he'll have IJ and he'll have IJ there, but it's easier just to do it this way. I put the 2 so you know you're just looking at. If you wanted the insertion loss 2,1, you simply put S21 in there, take the magnitude of it, the log of it, and put minus 20 in front of it. And you have the insertion loss. If you wanted for the 1,2, then you just put S12 here, take minus 20 times the log of it. That's just concepts, but they're used all the time. Okay, then after that we talk about shifting the reference plane. This is kind of interesting, and this is shown on page 566. I'm going to do this and then probably do some more problems, because by now you're wondering, what we're going to use all these concepts for, like return loss and things like this. I always say it's a measure of how good the circuit is performing. So this is on page 565 and 566. It's a shift in the reference plane. And the way it works is like this. If I have my little filter, whatever it is, and S parameters right here, and this is going to be S parameters for that system. But then I say that I'm actually going to be measuring, or I'm going to be using the device with the length L1 here, and I'm going to be using the device with the length L2 here. And what I want is the S parameters of the new port 1 would be here now. Port 1 is shifted by this much, and port 2 would be here. So here's where my measurement's going to be. This is going to be my V2 prime. This is going to be my V1 prime. But I've had a device, but now I add these links to it. And the reason this is important is when you're dealing with an S parameter measurement of something, if you want the S parameters of this matrix, you have to use cables to attach to it. The cables have a given length. And this will have a given value of beta 2. That will be beta 1. This will be beta 2. So now just think about this. Any kind of device, you don't have a contact point that has no distance. There's got to be some cabling that goes through this. So this has to do with real measurements of S parameters. And when you're doing this, what happens is, and he shows this, I think, he shows like a real S parameter measurement on page 567. You have your books there. If you look there, you'll see he's got a device and he has 2 cables connected to it. And what they'll do is the computer will catalog all the values of the S parameters as he sweeps frequency. It will not be at just one frequency. He'll sweep over a range and he'll have the S parameters. So then, if you look at this right here, if I go ahead, I input a signal here, right, V1 plus. Well, as it moves through here, there's a phase change. phase change by the time it hits this point is going to be e to the minus j beta 1 times L1. You all follow me on that? Then as the signal gets through, there's also going to be a phase change here, and that total phase change by the time it gets here, I mean over this length I should say, would be e to the minus j beta 2 times L. Beta 1 L1, beta 2 L2. Don't follow me? That's just the phase difference. So think about this. When we take a look at S22 before, or better yet, S11. When we had S11, that was V1 minus over V1 plus, assuming V2 plus was 0, right? That was the definition of S11. So now, if you think about that, if we were right here, we would measure, if there was a matched piece, we would be measuring the actual value of S11, right? If I move out here, what happens? Now the signal has a phase change of e to the minus j beta on L1 to this point, then another phase change of e to the minus j beta 1 L1 to this point, right? So now when I look at the S parameter matrix for the, this is for the outer point called S prime. Now that's going to have S11, and it will have e to the minus j 2 beta 1 L1 because of the phase change involved there. And this is shown in his book. Yeah, he calls it S prime, so equation 10.35. And just understand this, the only thing he's doing is now accounting for the phase difference, because the wave came down here before it hit here. Then you have to multiply by the S parameter, and then there was a continual phase change when it got back here. So that means the actual these S prime parameters, and this would be for the outer region here. I'm going to call that the S prime region from here to here would be this. And if you think about it also, when I'm looking here, if I was right there, it would just be S22 if I was looking with a maximum. But because now the wave is actually going to have a phase shift from the time it enters here of e to the minus j beta 2 L2, and another phase change by the time it gets back from reflecting, you're going to have S22, the original S22, times e to the minus j 2 beta 2 L2. Usually beta 1 and L1 and beta 2 are the same. Now, what you're doing is this. You're going to measure these things, and then you're going to extract the actual S parameters by getting rid of the effects of that cable, the phase shifts. Y'all follow me in this class? So now these two here, S21 and S12, they're going to be affected, and now the phase change will be from here to here would just be e to the minus j beta 1 L1 plus, or really plus e to the minus j beta 2 L2, or it would be e to the minus j beta 2 L2 plus beta 1 L1. If beta 1 is equal to beta 2, you can just take them out in front, put e to the minus j beta, and just L1 plus L2. But and down here will be the same. E to the minus j beta 2 L2 plus beta 1 L1. Now, if this is what you measure, and you want just the S parameters, it's very easy to get them out of there. You simply take whatever the S parameters you have there in the measurements and multiply by e to the j beta, j2 beta 1 L1. Beta is a function of frequency. So one thing you have to understand is, as you raster the frequency, you have to change the value of beta every time. Because beta is 2 pi over lambda, and lambda will change versus frequency. And the same here, but you can extract these values very quickly. In most modern programs, once you give it the lead length and stuff like this, they can just pop out the actual S parameters without any problem. I mean, the modern equipment. Has anybody ever done an S parameter measurement? You have it for what?
I'm in the small silent program. I do, it's,
Did you do cable, so you accounted for the length of the cable system?
yes.
Did you use, what spectrum, I mean, what network analyzer did you use?
I don't know what it's called. It's the one that's in the anechoic chamber.
Is it Hewlett Packard? And over what frequency range? X-band or what?
Up to like 11 gigahertz.
All right. X-band is technically about 6 to 12 gigahertz. So if you're running, you're over the lower bands of X-band, you're probably over X band, you started at somewhere around 8, remember?
I started a little bit lower than that, just to.
7, 6, normally they start about 6 and raster all the way up to about 10, but usually not to 11, at least.
I don't know, I probably said that.
Anyway, so he has a little experience with this. Some of you, almost guaranteed, if you're gonna be doing anything that has to do with antennas, radar, matter of fact, designing Wi-Fi devices, anything like that, you're gonna be doing S parameter measurements. It is important, and you have to at least appreciate what it's about, and those cables make a big difference, by the way. That's the thing you have to always account for. Okay, so that's shift and reference plane. I'm going to mention, the last thing is couplers, and then I'm going to start doing problems. So, and this is something that's used all the time in radar and in a lot of different communication packages, and I'll show you why. So, here's the idea behind it, and it's really a 3-port problem, but I want to show you, give you an idea of why it's important. So, here's a coupler in a nutshell, and he just has the standard ones. It's called a circulator, or the one he's showing is a 3-port, it's a circulator. So you're going to have something, the way he draws is, he draws it. These are not circular in general, but he uses this. All right, so this is port 1. Just write this down, and you'll understand. This is port 2. And this is port 3. Assume all these things have a characteristic impedance of Z0. Okay, so there's no, port 1 would have an incoming signal of V1 plus and outgoing signal of V1 minus. Do y'all follow me in this class? I'm not going to write them all down, but y'all follow me? Okay, now here's the deal. For port 1, assume this is a power source. He wants all of that to go to that port, and none of it to go to this port. Y'all with me? And then he wants any signal received at this port, so think of this as your antenna. Right? Everything that's transmitted, he wants launched, and nothing, but now anything that comes back, he wants it only to feed into port 2. Y'all follow me? That usually is as far as it gets, and that's a transceiver. Everything launched this way, it's thrown out. Anything coming back this way, it's the port 2. That's usually where it stops. But also with the true circulator, then everything from port 2 or 3 that comes in goes to port 1. Y'all follow me? That's the purpose of a circulator. And you should, in your mind, you should ask, well, how do they build those things? What devices do that? Anybody have an idea? Some of you might. They use magnetic materials. And what the reason is, do y'all remember how you had something that if you had a B field and you had a charge flying through it, it would bend one way if it's positive, the other way if it's negative, right? Well, what they'll do is they'll have magnetic materials so that as this electromagnetic wave is propagating and they're generating small amounts of it will bend it one way if it's coming into the port, and if it's going, anything, put it this way, everything coming in will bend one way, and everything coming into that port, everything going to the port will bend into the port. And it's hard to understand this, but it has to do with magnetic stuff. I could probably show you a video clip of some of this stuff. That's how they make these things. And they're supposed to be low loss, but whenever you have magnetic materials, they're never really low. You're going to pay for it. They're going to heat up. But circulators are used all the time. This is one of the things. So now we need the S parameters for this. Let's start by doing it this way. He's going to go ahead and he'll show you the basic diagram of that. But here's what the ideal is. They want all these ports matched, so they want the reflection coefficients on all of them to be 0. Y'all understand that? So S11 equals S22 equals S33 equals 0. They don't want anything at all reflected. If it was reflected, you already lost energy there. So then, when you take a look at this, if V1 comes in here, just look at this, I got V1 plus, they want all of it to come out here. V2 minus, right? So when I take a look at V2 minus, right? over V1 plus, that is S21, isn't it? By definition. You all agree with that? If you don't remember that, that's okay. You've just been exposed to this. But that's what it is. So that would be equal to 1. You all follow me? And the reason is that that's the definition, S21. It's assuming that everything's matched otherwise. Now, what else? Well, I want everything coming in, so anything coming in, any V2 plus, coming into this port to come out port 3. So I want V3 minus over V2 plus to be equal to 1, and that's going to be equal to what? S32, isn't it? Y'all follow me? You understand how I'm getting this, by the way? Whenever I'm talking about like 2, 1, if you remember the way I did it, I had V1 minus is equal to S11 V1 plus S12 V2 plus, right? And then V2 minus is equal to S21 V1 plus S22 V2 plus, right? Y'all follow me? You can keep adding. We can say it's plus S13 times V3 plus S23 V3 plus, and you can have V3 minus is equal to S31 V1 plus S32 times V2 plus S33 times V3 plus. I'm just showing you how you could, that I can do it. Therefore, I can figure out whenever I look at S31, right, it's V3 minus over V1 plus. Y'all follow me? I'm just showing you. Assuming it's all matched over there. Okay, so what about this one? What is V3 minus over V2 plus? Right there, isn't it? We want that to be 1, don't we, class, by definition? I want everything coming in here to come out there. So this is going to be 1. What else? In his definition, everything coming in this port comes out port 1. So that would be 1. That's V1 minus, right, over V3 plus. That's this, isn't it? So that's S13 is equal to 1 as well. Do you all agree with everything else is 0? All right, it's matched every which way. There's no reflection coefficient for an ideal circulator. So that means the S parameter matrix for this one's going to be what? Well, all the reflection coefficients are 0. Diagonal elements are 0. Next, I take a look and I see S21 is 1. That's a 1 down here. What else do I see? S32 is 1. And that's this one is 1. That's a 0. And S13 is 1. So that's up here. And everything else 0. And that's the S parameter matrix for an ideal circulator. And you should show that, and that's equation 10.36 if you take it. Can you all see that in the text class? Now I got to tell you one thing. It's never that good. Normally they do it in dB. They're going to take the dB values of all these things. Well, if you have a 1, so 20 times the log of 1. What's the log of 1? 0, right? So that would be a 0. That would be a 0. That would be a 0. The other ones, you're going to get something where they're going to have dB values that are very large, typically, to show what really is very small, to show that it's pretty well matched. Y'all follow me on that? It'll be negative cajillions kind of stuff. And you'll see that in time. You'll see it as we, actually it will be positive, but you'll see this as we do some problems. Now I'm going to get on to some problems. I got a few minutes left, and I want to go to the back of the book for these. So the first set of problems I want to do, how many have your book here? Okay. I'm going to put these up here, and I want to just ask you some questions before we start brute forcing. And I hope this helps. Is anything going on today of importance? Any test? Nothing for that one. Our first game's tonight? What time? 6 o'clock. Are you guys going?
Oh, yeah. I'll watch on TV.
No, I actually think basketball, Bruce Pearl, that new era, is more exciting than football. I mean,
It is, yeah.
especially when they get Bobby going nuts. Crazy. So here's the first one they show. It's two short circuits like this. So just understand it. There's no resistance. It's just a short. This is port 1. And this is port 2. All right, now I want you to just think about this. Look at it and think about it. We're assuming this is Z naught, and this is Z naught. Now just hear me. What is, first of all, is it a reciprocal network? Does it look the same either way? Yes. Don't even bother doing that. S times S. It's a waste of time. Next thing is, what's the reflection coefficient of port 1? Which will be at port 2? Just look. I'm coming from Z naught. Where am I going?
To the same thing.
What's the reflection coefficient?
0.
0. That's a no-brainer. Now, what is S21? That's V2 minus over V1 plus by inspection. How much of this signal gets over here? All of it is 1. What is S12? Which is really coming from this way. How much of that signal gets over there? Class? 1. That's a no-brainer, all right? So you've got zeros on the diagonal, 1s at the corners, right? It would look like this, right? For this one, it's 0, 0, 1, 1. That would be the S parameters for this one. Keep the thought. Remember, I'm just trying to make sure you get thinking the right way about this thing. What if you have this? Here's port 1 and port 2. No connection at all. No connection. All right? Just look now. Think. When I look at this, what would the reflection coefficient? First, is it a symmetric network or reciprocal? Yes. Isn't it just by inspection? Looks the same thing. So what is the reflection coefficient here? What is S11? Take a look. It would be going into 0 or an open circuit. Just listen to me. An open circuit is infinite resistance, right? So infinity minus something finite over infinity plus something finite is 1. What is S22? The same thing, right? Arguments of symmetry. All right, now, what is S12 or S21?
0.
It is 0 for one reason. There's no possible way any signal from port 1 can get to port 2. It's an open circuit. Y'all follow me? So that's another easy one. Next one, and these are all in his book. Next one he does is this. These are just to get you thinking right. And then he has, how does he do this? He has one cap. Oh yeah. So then he has, this is the one that I got a kick out of. Oh, it's a Wentworth problem. So here's this port 2, but he shorts port 2 out, right? So this is port 1. This is port 2. I'll leave it after this. Just work with me on this one. Now take one look. What is S11? That's an open circuit. Infinity minus something finite over infinity plus some is going to be 1, right? Now, what's the transmission coefficient there? 0. Nothing gets over there, right? Absolutely nothing. I mean, you might as well just do this. S21 is 0. Just leave it like that. There is no connection. No way any signal from here can get over there. Now, what's the reflection coefficient over here? S22 is going to be minus 1. Exactly. That's a short circuit. So I go from 0 minus Z naught over 0 plus Z naught is going to be minus 1. And what is S12? 0 as well. No connection from the primary to the, there's no way port 1 can affect port 2 in any way. Y'all follow? Now that's a simple way of thinking of this, but it's very useful that we see this the first time. Because then things starts making sense. And I'm out of time. I'm going to give you a bunch of problems. Please do them for Wednesday so we can have a meaningful discussion. You won't cram on Thursday and then have a problem on quiz. Okay. Great. Any extras, class?
I wrote the L in the same.